Now, before going to the matrix methods of structure analysis, first we have the overall view of the energy methods, because based on those energy methods only the matrix methods have come. So we'll see what are the energy methods available, and from them how the force method or flexibility method and displacement methods they are derived, we will see. Okay, now we'll see the 14th topic, energy methods. First point is energy. I have told you when we have taken about the strain energy chapter, gradual applied load, suddenly applied load, impact loading, and also we have taken Castigliano's theorem 1, 2 I have given. Based on Castigliano's theorem 2, we found the deflections in the trusses, relative displacement, absolute deflection, and rotation of a member for statically determinate structures we have found from the energy, strain energy stored in the members. PKL by AE we have taken, then we have used the same strain energy stored in the structure for a frame. We found the displacements also, integral of mx m dx by EI. Now we will have the complete bird's eye view of the energy methods available for linear elastic structures and non-linear elastic structures. Okay, so now energy, if at all you write energy in terms of strains, we call it as strain energy. If you write energy in terms of loads or stresses, we call it as stress energy. Also, we call it as complementary energy. Okay, so we'll see first that. First thing is strain energy. Strain energy means energy expressed in terms of strains or displacements. Then we have stress energy. Energy expressed in terms of the forces or stresses. This stress energy, we also call it as complementary energy. Stress energy, complementary energy both mean the same. Next, what is strain energy? It is expressed in terms of displacements. This I have given you. What is that in terms of displacements means? I have given you U is equal to, for a single member we have derived delta square AE by 2L. Then Castigliano's theorem 1 we have applied dou U by dou delta, then AE by L we got it. That AE by L we called it as stiffness in the energy chapter, in strain energy chapter. So strain energy is expressed in terms of displacements in this fashion. For a single member you have given, if a big structure is there, in terms of different displacements, we have to write the energy in terms of the displacements. Okay. So delta square AE by L. Now this energy, strain energy, it is related to displacement and stiffness methods. Okay. So from the strain energy, we get the displacement and stiffness methods. Now let us see stress energy or complementary energy. As I told you earlier, it is expressed in terms of forces. How we have expressed in terms of forces? In terms of forces or in terms of loads? whatever way you take it. What you have written? Strain energy, you have written P square L by 2AE. Strain energy you can express in terms of the displacements, in terms of the forces, in terms of the stresses also you have three expressions. So if you write like this, we call it as complementary energy, P square L by 2AE. So this complementary energy is related to force and flexibility methods. Force and flexibility methods. Okay. Now let us see how the complementary energy is derived. If we take load versus deflection curve, say, for a non-linear elastic material, it will go like this. Load versus deflection curve. For non-linear means load versus deflection is not a linear curve, some other curve. Non-linear elastic material. This is what you have learned in strength of materials. Then load versus deflection curve for linear elastic material. Load versus deflection curve for linear elastic material. Okay. Now let us see how stress energy, strain energy are defined. Load versus deflection curve and x-axis. Area under that we call it as strain energy. That's what we have learned. If we take this area of load versus deflection curve, this we call it as strain energy. Next, load versus deflection curve and load axis. If I take this area, this we call it as stress energy or complementary energy. This area complementary energy or stress energy, because you are expressing in terms of forces. So why we call it as complementary energy? In a geometric sense, if you add strain energy area and complementary energy area, you will get a rectangle. If you say complementary angles, then what is complementary angle means? Angles means the sum of the two angles is 90 degrees. Similar to that, here is complementary areas means sum of the areas must form like a rectangle. So that's why this is a complementary area to this one, because sum them you will get a rectangle. If you have a non-linear elastic material, complementary energy, this energy are not same. Okay. If you take linear elastic material, curve goes like this. If you take the area, say something like this. This curve we can extend it wherever area if you take it. This area we call it as strain energy, area of load versus deflection curve. This is strain energy. Now this area will become complementary energy, because this is complementing the other area. So this we call it as complementary energy. Okay. For linear elastic material. Now you see why we want to call it as complementary is in a geometric sense it is complementary means. This is the reason. In a geometric sense, stress energy is is a complement of strain energy because it completes rectangle. Okay, it completes a rectangle. That's what you have studied in your mathematics also. Complementary angles are complementary areas or complementary regions. So if this is one curve means inverse of that curve area is like that. For a linear elastic material, complementary energy, strain energy, both of them are same. But whereas here, these are different. Okay, not. For linear elastic material, strain energy and complementary energy are equal. Okay, now this is a basic definition of strain energy, complementary energy. Under what circumstances they are equal and under what circumstances they are not equal. And on the strain energy, we have Castigliano's theorem 1. On complementary energies, we have Crotty-Engesar theorem and Castigliano's theorem 2. They are based on complementary energies. Castigliano's theorem 2, as I told you, because strain energy, complementary energy are same, then we can write Castigliano's theorem 2 is applicable to linear elastic materials only. Theorem 1 you can apply for linear, non-linear elastic materials. First, that's what earlier I told you. Now I am giving you the bird's eye view of entire energy methods available. So, strain energy, stress energy difference you have known. Sometimes it will be equal. No, linear elastic materials, non-linear means those magnitudes, complementary energy magnitude, strain energy magnitudes will be different. Okay. Now, this is what you have studied. Linear elastic, under what circumstances principle of superposition is applicable? You have strength of materials, first chapter is that only. You must have a linear elastic material and also deformations must be small for the principle of superposition to apply. Even if you have a linear elastic material but large deformations are there, you cannot apply principle of superposition because if you take a rubber bar, let us say, whose diameter is say 1 centimeter, you pull it so long, say 1 meter long you pull it, so 1 centimeter will become 1 mm. Now stress is now function of load and area. So you, as the load increases, stress will not increase linearly because the stress is a function of area also now. Area is continuously changing. So then non-linearity will exist because the geometry is changing. So for large deformations, geometry of the structure means cross-sectional area or shape, they change and they influence the action of the loads also. Okay, action of loads means stress values will be different, means deformations magnitudes also will be different. So let us see your second point. This is your second concept. What you have studied in strength of materials. Linear elastic material with small deformations. Principle of superposition is applicable. Principle of superposition is applicable. See, small deformations must be there, though it is a linear elastic material. Supposing that if you have linear elastic material with large deformation, with large deformations, principle of superposition superposition cannot be applied. Why? Because when deformations are large, cross-sectional area changes. So, stress becomes a function of load and area. A function of load and area. Stress will not vary linearly with load, as cross-sectional area is continuously changing. This is what you have learnt. Small deformations are applicable, large deformations you cannot apply, because stress means stress is directly proportional to the load. We cannot write that, because the stress, as the load increases, stress increases, will not increase linearly, because area also is there. Area is also a very variable quantity. So this you cannot apply. So accordingly, non-linear, this means geometric non-linearity. Linear elastic means material is, the stress strain curve is linear, but because of the large deformations, geometry changes, then non-linearity will come. So you have two types of non-linearities. Material non-linearity, that means basically the stress versus strain itself is not linear. Second one is geometric non-linearity. Geometric non-linearity exists because of the large deformations in the structure. Okay, so that we take it as third point. Types of non-linearity. First, material non-linearity. Material non-linearity and geometric non-linearity. Material non-linearity means material having non-linear stress strain curve. Stress strain curve. Now, geometric non-linearity occurs when when deformations are large. This is what will happen. Large deformations change the action of applied load. Action of applied load. That means stress magnitude non-linearly it varies action of the applied loads. Now, in both cases, whether it is material nonlinear or geometric nonlinear, but they are elastic structures only. That means when load is applied, it deforms. Load is removed, it will come back to its original position. Both cases. But that stress versus strain will not vary linearly because of these two reasons. But in both cases, material is elastic. Engineering mechanics, sir might have told you, law of conservation of energy is applicable only when you have perfectly elastic materials. So, for the energy theorems, where you use the law of conservation of energy, for those energy theorems to be applicable, they must be elastic. Okay. So, material is elastic. Otherwise, we cannot apply any energy theorem. Or law of conservation of energy. That's the reason why whatever energy theorems that we study, they are applicable to elastic materials only. That elastic material can be linear or non-linear elastic, because that law of conservation of energy will not worry whether material is elastic or inelastic. So, after this, you have studied fourth concept, Castigliano's theorem 1. This is what I have explained about the Castigliano's theorem 1. We'll see what it is. Castigliano's theorem 1. What I have told you here was, if you want to find force or resistance at any point in a structure, first derivative of strain energy with respect to displacement at any point in the structure gives you load at that point or resistance at that point in the direction of the displacement. This is what we have written already. So, if you want to apply this Castigliano's theorem 1, U, that means strain, U is strain energy, it must be expressed in terms of displacements only. If U is in terms of displacements, then I can differentiate it with respect to displacement, any displacement. Supposing that in a big structure, this one displacement I have given you in the axial loading case, in a big structure 10 displacements are happening. So, in terms of 10 displacements, you will write the strain energy. At any one point, if you want to find the load, then entire strain energy stored first partial derivative of energy with respect to delta 1 say. Then you will get load P1. Dou U by dou delta 2, you will get P2. Force at the second point, like that. So, for that, U must be expressed in terms of the displacements, and it is applicable to linear elastic, non-linear elastic structures, because this comes from the law of conservation of energy. So in this first point is, this U is strain energy. Strain energy must be expressed in terms of displacements only. In terms of displacements only. If I want to apply theorem 1, then applicable to, it is applicable to linear elastic, linear and non-linear elastic materials. Then non-elastic materials, that is both material non-linearity and geometric non-linearity. If a structure has or material has geometric nonlinearity and also material nonlinearity, still we can apply Castigliano's theorem 1. Because when you are differentiating the strain energy with respect to displacement, you get the load, and that comes from the law of conservation of energy, the derivation. So whether it is linear or nonlinear, you can apply theorem 1. Right, the reason, because law of conservation of energy is applicable whether material is linear or non-linear. This is theorem 1. Then on the strain energy, this is the Castigliano's theorem 1. On complementary energy, we have another theorem, Crotty-Engesar theorem, that we take it as concept 5. They have given on the complementary energy principles. Complementary energy has given. This is Crotty Engesar theorem. What it tells you is, displacement at any point is equal to first partial derivative of complementary energy with respect to load at any point gives you displacement at that point in the direction of the load. But if I want to use this one, U must be complementary energy. U star is equal to not strain energy, it is complementary energy. So first derivative of complementary energy with respect to load at any point in a structure gives you displacement at that point in the direction of the load. Okay. Then such U star, first point is complementary strain energy or complementary energy U star must be expressed in terms of loads only. If U star is expressed in terms of loads, then I can differentiate with respect to load to get the displacement. Then applicability. Valid for linear and non-linear elastic structures. In the non-linear elastic structures, only material non-linearity is there, you can apply. If geometric non-linearity is there, where large deformations are there, that law of complementary energy will not be conserved. Some of the energy is lost during the loading process. So we cannot, since energy is not conserved, we cannot apply where geometric nonlinearity is present. Valid for linear and nonlinear elastic structures. That means material nonlinearity only, but not for geometric nonlinear structures. Why? Because complementary energy is not conserved if geometric nonlinearities are present. Okay. So on strain energy, you have Castigliano's theorem 1. On complementary energy, you have Crotty-Engesar theorem. Next, if you have, supposing that linear elastic structures are there. For linear elastic structures, complementary energy, strain energy are same, I said. Then I can write dou u by dou p also, but material must be linear elastic structure. Note, for linear elastic structures, complementary energy is equal to strain energy. Complementary energy is equal to strain energy. Because triangle area means when it forms a rectangle, it will be two areas will have to be same. So U star is equal to U. So we can write delta is equal to dou U by dou P. Now this is what I have told about the Castigliano's theorem too. So then U now here is strain energy. Valid only, that's why for linear elastic structures. Castigliano's theorem 2 he has derived only for linear elastic structures. Okay. Delta is equal to dou U by dou P. Then this equation becomes Castigliano's theorem 2. That means Castigliano's theorem 2 is a particular case of Crotty-Engesar theorem. Crotty-Engesar theorem is applicable to linear nonlinear structures. If it is applied to linear elastic structures, it is same as Castigliano's theorem. theorem 2. So theorem 2 is applicable to linear elastic structures only. Okay. So actually there uh, your Castigliano's theorem, he has used strain energy, you differentiated with respect to P. That means U star will become U. As per Crotty-Engelsaer theorem, dou U star by dou P only you have to write. But U star is nothing but U only. So this reduces to Castigliano's theorem too. Next, sixth point. This we write it as a instead of 5. This we write make it as sixth point. We'll take it as seventh point now. Seventh point is when you are dealing with strain energy and Castigliano's theorem 1, the method that you get is a set of equilibrium equations. So we call them as equilibrium method of analysis because you get equilibrium equations in terms of unknown displacements. We also call it as displacement method. For linear elastic structures, the displacement method becomes a stiffness method of analysis. Okay, so this is what we have told you earlier. Strain energy and Castigliano's theorem. Theorem 1 give displacement method. Okay, from this displacement method uses strain energy, Castigliano's theorem 1. This theorem gives a set of equilibrium equations. How that set of equilibrium equations in matrix methods, when you are taking the displacement method, those set of equilibrium equations we will write. Okay, now you understand that it will give you a set of equilibrium equations. For a set of equilibrium equations for indeterminate structures. Okay, if it is, that means strain energy and theorem 1, if it is applied to, you can apply nonlinear also. If at all you apply to linear elastic structures, it is called stiffness method. It's called stiffness method. So displacement method is a general term which uses this and this applicable to linear, nonlinear elastic structures. If at all theorem 1 you apply to linear elastic structures, what you get is called stiffness method of analysis. How this one, how the equilibrium equations look like is P1. Force at first coordinate if you want, first derivative of energy with respect to the displacement, delta d1 let us say. With respect to displacement, if I take it, I get first one. Similarly, this is like equilibrium equation. You are getting force expression. Then P2, force at coordinate 2 or at second point is equal to first derivative of strain energy with respect to displacement or secondary displacement. If you differentiate it, you will get a second equilibrium equation. Solve all such equilibrium equations, you will get all the displacements. Okay. So, these are equilibrium equations. Where D1 and D2 are displacements. So, in terms of displacements, D1, D2, etc. displacements, energy you have to write. Then differentiate it. Displacements where forces P1 and P2 are acting. Okay. So, this is about the strain energy. Again, we will see that from this, if at all dou u by dou d1 becomes 0, or it should be some force, dou u by dou d1, you will get a force like this. Here also some force you will get it. In the complementary energy cases, where if that value dou u by dou x etc. becomes 0, then we call it as principle of minimum complementary energy, principle of minimum strain energy, etc. We'll again list out those points. This is what is the case. P1, P2, if you differentiate with respect to first displacement, if your energy is partially differentiated with respect to second displacement, you will get the second force. So, like that, so 10 displacements are there, means 10 equilibrium equations you will get. Solve them, you will get the displacements. Okay. Next, this is about the strain energy, how we use them in the energy methods. Now, complementary energy, how we use. Now, eighth point is complementary energy and Crotty-Engesar theorem gives you force method because they give you a set of compatibility conditions. So, eighth point, complementary energy and Crotty-Engesar theorem give force method of analysis. Force method of analysis. Now, this theorem, that means Crotty-Engesar theorem, gives a set of compatibility conditions. How to get that set of compatibility conditions in the flexibility matrix method we will see, because flexibility matrix method is applied to linear elastic structures. If it is non-linear, you will use the Engesar theorem. So, it is also called compatibility method because you are getting a set of compatibility conditions. Compatibility method of analysis. Now, for linear elastic structures, the same force method is called flexibility method, because when you are getting the compatibility conditions, all flexibilities will come. What is that flexibility? Strength of materials you have studied. AE, product is called axial rigidity. Axial rigidity by L. AE by L is called axial stiffness. Inverse of that, L by AE is called axial flexibility or simply flexibility. Such type of flexibilities will come by differentiating it. So we get the, or we call it as flexibility method or Maxwell Moore method, because Maxwell and Moore also have given for the linear elastic structures. So this flexibility method or Maxwell Moore method both mean the same. In this case, what are the compatibility conditions? If you want to find displacement at first point, first derivative of strain energy by force at that point. Now see, potential energy, if you use complementary energy, you will get Crotty-Angesar theorem. If you put strain energy, you will get Castigliano's theorem too. That is the only difference. For linear elastic, complementary, strain energy same. So Crotty-Angesar theorem becomes Castigliano's theorem too. So delta dou u by dou p1. This is one compatibility condition, because the relationship between the displacements you will get. Delta 2 is equal to dou u by dou p2. Okay, etc. or compatibility conditions. Okay, now you see, in this case, dou u by dou p1 or dou u star by dou p1 will give you displacement. If the displacement happens to be 0, say p1, p2, etc. are some redundant forces, then what happens? Dou u by dou p 0 means maximum minimum principles you have studied in the mathematics. For any quantity to be maximum or minimum, its first derivative must be 0. So dou u by dou p is 0, let us say, then u will be either maximum or minimum. If you have a stable structure, potential energy is minimum, that means strain energy stored is also minimum. So you will get dou u star by dou p is equal to 0, means that once it becomes 0, means if the displacement happens to be 0, then Crotty-Angesar theorem will become principle of minimum complementary energy. Here also dou u by dou p2, this is Castigliano's theorem too. Instead of writing the complementary energy, if you write the strain energy, differentiate it with respect to load. If that becomes 0, displacement is 0. But mathematically you have studied dou u by dou p is 0, means u will be either maximum or minimum. Because strain energy will have to be minimum for a stable structure, then you will get the principle of minimum strain energy, because dou u by dou p is equal to 0 means minimum strain energy. That becomes minimum strain energy provided this delta must become 0. That means at the redundant reactions, if the displacements are 0, then if you the dou u by dou x or dou u by dou x1, dou x2, etc., when you differentiate it, if it becomes 0, then it becomes principle of minimum strain energy. So principle of minimum strain energy is a particular case of Castigliano's theorem 2, where displacement happens to become 0. That point will write ninth point now. Now, in the force method, I told you we express the energy. We write the complementary energy in terms of the forces. Then we use Crotty-Angesar theorem to get a set of compatibility equations. Solve those compatibility conditions to get the unknown redundant forces, if at all you deal with the statically indeterminate structure. Supposing that if the redundant reactions, supposing the support reactions happen to be redundants, then those redundant reactions, they don't displace. So the displacement is 0. So first derivative of complementary strain energy with respect to that redundant reaction should give the displacement. If the displacement is 0, then dou u by dou x is equal to 0 you have to write. If at all if the redundants do not undergo any displacements, then dou u by dou x, Crotty-Angesar theorem, dou u by dou x is equal to 0, you will get it. Then we call it as principle of minimum complementary energy. If at all you have a linear elastic structure, complementary energy, strain energy will be same. Then the principle of complementary energy becomes principle of minimum strain energy. Okay, like that. Strain energy, and then principle of minimum strain energy will become a particular case of Castigliano's theorem too. Okay. Now these points we have given, we will write those points also so that more clarity will be there. 8 points I think we have given. 9th point we will see. This is what we do. In force method, we express complementary energy U star as a function of redundant forces. As a function of redundant forces means U star must be written in terms of the forces, not the displacements. And those forces are redundant forces. Redundant forces. Then use Crotty-Engesar theorem. What is that Engesar theorem? Dou U star by dou x is equal to some displacement is there, you will get displacement. If it becomes 0, let it become 0. Dou U by dou Crotty-Engesar theorem to obtain equations of compatibility. To obtain equations of compatibility. Solve these equations, that compatibility equations, how to solve them, etc. We see the examples in the flexibility matrix method. We express them in systematic manner in the matrix methods. There I will write a set of compatibility conditions. Equations of compatibility. Solve these equations to get redundant forces. This Crotty-Engesar theorem and complementary energy, because you are applying, you can apply this energy theorem for the linear and non-linear elastic structures. That non-linear must be material non-linearity only. Geometric non-linear structures, you cannot apply this principle forces. So this is applicable to linear and material non-linear structures. Enough material non-linear structures means geometric non-linearity you cannot apply. Next, a particular case in this one is like this. First point, a particular case of force method where there are no displacements, let us say. There are no displacements corresponding to redundants. Corresponding to redundant forces. When that will happen, no displacement corresponding to redundant force. If at all you are taking support reaction as a redundant force, then complementary energy you are writing. If you differentiate the entire energy with respect to that redundant reaction, what's the value? It should be 0 only. Such cases is a particular case where the redundant forces wherever they are acting, displacements are 0 say, then we can write dou u star by dou x1. This is a support reaction VA, let us say. Then it will become 0. And support reaction at B you have taken dou x2, means another support reaction, let us say. That means x1 and x2 are support reactions where there are no displacements at all. So differentiating with respect to x, that means force, it should be 0. Then it becomes, if at all, if the structure is in stable equilibrium, strain energy stored is minimum. I have told you the types of equilibrium in engineering mechanics when they have discussed. Supposing that you have a structure like this, some load W, this is a stable equilibrium, right? Stable equilibrium means what? Strength of material sir might have told you in the columns and struts chapter. Types of equilibrium. Stable equilibrium means if a body which is in equilibrium, if it is displaced, then if it comes back to its original position, it is called stable equilibrium. Example of that is this one. Even steel structures also I explained. You have small bowl, keep a stone there, give a small displacement. It will oscillate, come back again to the same position. That is called stable equilibrium. If you take any datum line here, say its potential energy is minimum. Energy stored now in this one is it is minimum energy level, it will be there. Okay, that means here dou u by dou x, first derivative is equal to 0, implies that potential the complementary energy in this case, it will be a minimum value. Then this is this represents principle of minimum complementary energy. Okay, so for a structure, for a structure to be in stable equilibrium, stable equilibrium is that stable equilibrium, U star is minimum. You see energy stored is minimum here. Any other position energy is more. Potential energy is more. Comes to lowest point means potential energy is minimum. Corresponding complementary energy, strain energy, everything is minimum. Stable equilibrium, U star is minimum. So dou U star by dou x is equal to 0 represents principle of minimum, principle of minimum complementary energy. This is the principle of minimum complementary energy. Okay. Now, what this tells you is, second point, principle of minimum complementary energy states that the redundant forces for a stable structure force for a stable structure should have values such that the complementary energy is minimum. Complementary energy is minimum. That means U star will be minimum. For it to be minimum, x value should be such that dou u by dou x you should get 0. Like that, the x value will take up. but this is provided there are no displacements in the redundant reaction location. That means when you are dealing with the support reactions, etc., where there are no displacements, your principle of the complementary energy will come into picture. That means your Crotty-Engelser theorem becomes principle of minimum complementary energy. So this is, it will a particular case, that's all, where dou U by dou x is equal to 0. If displacement is there, then delta you will get dou U by dou x1 is nothing but some delta 1 displacement. Actually this one you should have written delta 1 displacement at first location, let us say dou U by dou x1. If it becomes 0, then it becomes principle of minimum complementary energy. If not, simply Engelser theorem, that's all. So minimum complementary energy is a particular case of Crotty-Engelser theorem. So provided there are no displacements, corresponding to redundant reactions, corresponding to redundants in the original structure. Okay, no displacements will be there, then only energy stored is minimum. The values will be such that x value will be value such that complementary energy is a minimum value. Supposing that if at all you have a linear elastic structure, I can replace complementary energy with the strain energy. Then it will reduce to minimum complementary energy principle reduces to principle of minimum strain energy itself. So for a linear elastic structure, complementary energy and strain energy, this I gave in the note 1, and strain energy are same. Then principle of minimum complementary energy, minimum complementary energy reduces to principle of minimum strain energy. Again, principle of minimum strain energy is a particular case of principle of minimum complementary energy. Complementary energy principle is applicable to linear structures, material non-linear elastic structures also you can take up. If at all there is no material non-linearity, it is a linear elastic structure, then it will become complementary energy and strain energy are same. Then I can write a complementary energy, principle of complementary energy or principle of minimum strain energy. I can use this word only when you have a linear elastic structure. For such cases only complementary energy, strain energy are same. Now this is the complete information regarding the complementary energy Crotty-Engelser theorem. In the process, if at all the derivative becomes 0, it becomes principle of minimum complementary energy. Now let us see the Castigliano's theorem 2, which is applicable to linear elastic structures. That will take it as 10th point. 10th point. Castigliano's theorem 2 is applicable to, what is that theorem 2? Delta is equal to displacement is equal to dou u by dou p. This is now theorem 2 means strain energy only. Okay, if the energy is differentiated with respect to load at any point, gives you displacement at that point. Okay, so he used the word strain energy. That means it is applicable to linear elastic structures. Theorem 2 is applicable to linear elastic structures. Where U is strain energy. But not complementary energy, because he derived only for that case, is applicable to linear elastic structures, for which principle of superposition applies. Just because you have a material which is linear elastic, large deformations are there, say, then you cannot apply principle of superposition because geometric nonlinearities will exist. So it should be linear elastic and deformations must be small. Only such cases you can apply principle of superposition. Such cases only Castigliano's theorem 2 is applicable. This cases no material nonlinearity and no geometric nonlinearity. These two things should not be there. Then we can replace U star with U. You can, for such cases, complementary energy can be replaced with strain energy. Then that strain energy he used here. This I have given you already. Crotty-Engelser theorem reduces to delta I, whatever you take it. This is Crotty-Engelser theorem. Will become Castigliano's theorem. Valid only for linear elastic structures only. I can write like this. Non-linear elastic structures, U star and U are not same. This equation delta is equal to dou U by dou P is known as Castigliano's theorem 2. That means a particular case of Crotty-Engelser theorem is Castigliano's theorem 2. In this again a particular case of Castigliano's theorem 2 where the displacement is 0, you will get principle of minimum strain energy. That will write the next point, where if U must be expressed in terms of loads only. In Castigliano's theorem 1, strain energy you have written, but you have that strain energy is expressed in terms of displacement. Here also strain energy only U, but that strain energy you have to express in terms of the forces. Linear elastic materials, whether you write a displacement or force, same. Result is same. U must be expressed in terms of loads only, then only you can differentiate it with respect to forces. Now, in this case, first point, note 1. If we have a redundant structure, let us say, delta 1, I can write it as dou U by dou P1. Displacement at second point, first partial derivative of energy with respect to load at the second point. Like this you can write, or dou U by dou x1, dou x2. x1 and x2, some redundant reactions which you wanted to find. At those redundant reactions, x1, x2, maybe support reactions you have taken, you are differentiating with respect to support reaction. Then if there is no displacement, then dou U by dou x also will become 0. So, if redundants, x1, x2 are redundant forces, x2 are redundant forces, say reactions. We'll write that point also, otherwise you may forget. Reaction is there means there will not be any displacement. If redundants do not undergo any displacement, that means there is no support settlement, say, then displacement is 0. Do not undergo any displacements, then I can write delta is equal to dou U by dou x is equal to 0. If at all this x does not undergo any displacement, delta dou U by dou x becomes 0. Now this expression tells you that first maximum minima principles. If dou U by dou x is 0, U can be either maximum or minimum. But if you have a stable equilibrium condition, U must be minimum. That means this will now become principle of minimum strain energy, which is a particular case of Castigliano's theorem too. So if the structure is in stable equilibrium, see this one, stable equilibrium, dou U by dou x is equal to 0 represents U has minimum value. Stable means minimum value, represents U has minimum value. So dou U by dou x, delta is equal to dou U by dou x is equal to 0, represents principle of minimum strain energy. See, principle of minimum strain energy comes from Castigliano's theorem 2. Theorem 2 again is a particular case of Crout-Yang-Essar theorem. Crout-Yang-Essar theorem corresponds to force method. That means minimum strain energy, minimum complementary energy, they come under force methods of analysis. Principle of minimum strain energy. Sometimes you call it as principle of least work or principle of least work. Both mean the same. Both mean same. Principle of minimum strain energy, principle of least work, both mean the same. So now, second point, what principle of minimum strain energy states is this one. Principle of minimum strain energy states that, comma, you see, this is for a linear elastic structure only. For a linear elastic structure, the redundant quantities, the redundant forces x1, x2, etc. have values such that strain energy stored such that strain energy stored is minimum. Again, provided there are no displacements corresponding to redundants in the original structure. If there are displacements, let us say, then Castigliano's theorem 2 simply gives you the displacement. If at all displacement becomes 0, your Castigliano's theorem 2 becomes principle of minimum strain energy. That means principle of minimum strain energy is a special case of Castigliano's theorem 2, where by differentiating at that point displacement is 0. That's all. If not 0, simply it is a Castigliano's theorem 2. That's all. Now, third point we can take it. Principle of minimum strain energy is a special case of what? For linear elastic structure. A special case of more general principle of minimum complementary energy. Minimum complementary energy applicable to linear, non-linear. If at all it is applicable to, if we are using it for linear elastic structures, minimum complementary energy becomes minimum strain energy. Again, this minimum strain energy is a particular case of the Castigliano's theorem 2. So here, this I remove. Now, we can also say that principle of minimum strain energy is a special case of Castigliano's theorem 2. In the general Castigliano's theorem 2 means delta is equal to dou u by dou x. Some delta you will get. If at all that delta happens to be 0, then we call it as principle of minimum strain energy. That means out of so many cases, if at all it becomes 0, it is called principle of minimum strain energy. So it is a particular case where delta becomes 0. So then Castigliano's theorem 2, you can call it as principle of minimum strain energy. So principle of minimum strain energy, principle of minimum complementary energy, Crotty-Angesar theorem, Castigliano's theorem 2, all come under force methods. Special case of Castigliano's theorem 2, where delta is equal to dou u by dou x is equal to 0. Okay. Now, this is the overall idea about the energy methods. So, the overall view is like this. Energy methods means you have two types of energy: strain energy, complementary energy. Strain energy means energy expressed in terms of displacements. If at all energy expressed in terms of the forces, we call it as complementary energy. That means as a load versus deflection curve with respect to y-axis, if you take area, complementary energy. Load versus deflection curve and x-axis you take and find the area, it is called strain energy. In terms of displacements, in terms of stresses. Then accordingly, Castigliano's theorem 1 came, applicable to linear, non-linear elastic structures. Theorem 1, when you applied, it is applicable to linear, non-linear. Non-linear means material non-linearity, geometric non-linearity you can apply. Okay, that means P is equal to dou u by dou delta. That you can apply for the all types of cases. Next came Crotty-Angesar theorem. That means those come under stiffness method of analysis or displacement method of analysis, because you get a set of equilibrium equations. That is called Castigliano's theorem 1. So theorem 1 gives you stiffness coefficients, or it comes under stiffness method of analysis or displacement method of analysis or equilibrium method of analysis, because you get a set of equilibrium equations and you get a set of stiffness coefficients. That's why. Then we have studied about the complementary energy. Related to complementary energy, you have two principles. One is Crotty-Angesar theorem, applicable to linear and material nonlinear elastic structures, but not for geometric nonlinear elastic structures. Then if you differentiate the complementary energy with respect to load, you will get the displacement. Then you have studied, if at all that displacement happens to be 0, then Crotty-Angesar theorem reduces to principle of minimum complementary energy. That's it. Next, Castigliano's theorem 2. He applied only for linear elastic structures. Strain energy stored with respect, if at all strain energy stored with respect to this force, if you differentiate it, you will get the displacement. That means for a linear elastic structures, Crotty-Angesar theorem becomes Castigliano's theorem 2. In the Castigliano's theorem 2 also, dou u by dou x when you are writing, if that partial derivative with respect to force, if at all that force becomes 0, differentiation, then dou u by dou x is equal to 0, you will get it. Then that we call it as principle of minimum strain energy, which is a particular case of the principle of complementary energy, we can take it, or Castigliano's theorem 2. This is the history of the energy methods. Minimum strain energy, principle of minimum strain energy, we also can call it as principle of least work. Okay, now having studied these methods, we list out what are the, in matrix methods, we sequentially list out what are the different types of methods of analysis. If the, we'll write here, Now we'll see the 15th topic. Matrix methods in structural analysis. Now Castigliano's theorem 1, Castigliano's theorem 2. Theorem 1 gives you a set of equilibrium equations. Theorem 2 gives you a set of compatibility conditions. If those compatibility conditions, if they are written in a matrix form and solved, then we call them as matrix methods. Okay. So whatever we have learned till now, we tabulate them for concepts. First one, methods to analyze indeterminate structures. So all the methods of analysis, whatever we have studied, all the methods of analysis can be classified into two types. Depending on the type of unknowns chosen. The type of unknowns chosen for the analysis. That is force method and displacement method. Now, force method and displacement method, they are general terms valid for linear elastic structures, non-linear elastic structures you can apply. If at all force method is applied to linear elastic structures, I told you it is called flexibility method. Displacement method, if at all you apply to the linear elastic structures, it becomes a stiffness method. Like that. Okay. So we will list out the characteristics of the two methods. First one, this is now second point. Force, flexibility, compatibility method. We call it as FFC, force, flexibility, compatibility. All are same. Only thing is more general term, linear elastic structures, general term. Means linear, non-linear elastic structures put together, force method, compatibility method. If at all it is applied to linear elastic, we call it as flexibility. Then displacement, stiffness, or equilibrium method. All mean the same. We call it as displacement, stiffness, equilibrium. Again, displacement, general term. Applicable to, if you say simply displacement method, it is a method where displacements are unknowns. If at all the structure is linear elastic, then we call it, that method becomes a stiffness method of analysis. That's all. Okay. So Let us see the characteristics. First one. In this, forces are unknowns. Forces are taken as unknowns. Forces means what? That is reaction or shear force or bending moment. Any one quantity. Shear force, bending moment, and equations are expressed in terms of these forces by using external equilibrium equations. I told you about the external equilibrium equations. Means you should be out of the structure. Sigma x 0, sigma y 0, sigma m 0 are external equilibrium equations. They are not sufficient because it is statically indeterminate structure. So additional equations you have to develop. They are called compatibility conditions. Okay. Second point. Additional equations called compatibility conditions. For linear elastic structures, Castigliano's theorem 2 will give compatibility conditions. For elastic but nonlinear elastic structures, only material nonlinear elastic structures, Crotty-Engesar theorem will give you the compatibility conditions. If at all energy method, if you take it, called compatibility conditions are developed to find the unknown forces. To find the unknown forces. Example. In strength of materials, we have taken so many compatibility conditions. For each chapter, one compatibility condition you have taken. They have all come under force method of analysis. In strength of materials, this part extension I am writing here. What you have learned in the first chapter is, first example I will explain here. This is what you have studied. This is in SOM. What is that you have studied in the first chapter is this one. Assume that you have a bar like this, subjected to some axial force P. A, B, C. There is a reaction here, left side HA, HB. Okay. What is the static indeterminacy? I have told you ds is equal to r minus s, 2 minus 1 degree. So 1 additional compatibility condition is required. So this is what you have analyzed. Equilibrium equation. First external equilibrium equations you have to use. Sigma x 0 minus HA minus HB plus P is equal to 0. Then compatibility condition you will write. Compatibility condition. A relationship between the deformations. What is the deformation? Elongation in AC is equal to contraction in CB. What is elongation in AC? HA, force is so much, HA into length of AC by AE, axial rigidity, must be equal to contraction HB into length of BC by AE. Strength of material sir told you that AE is called axial rigidity. Axial rigidity by length, we call it as axial stiffness. L by AE, reverse of axial stiffness, we call it as flexibility. So, if HA becomes 1, supposing that, then L by AE is called flexibility. Since you deal with the flexibilities, it is also called flexibility method. Okay. So, since forces are unknowns, it is a force method of analysis. In the arches, I have told you all that. Okay. Solving 1 and 2. Find HA and HB. So, this is a force method or compatibility method or method of consistent deformation. Consistent deformation also is like this. Then, second one, in flitched beams, in the theory of simple bending, after that the bending stresses chapter when you studied, flitched beams you have studied. Flitched beam means a beam of two different materials. Two unknowns will be there. Bending stress in wood, bending stress in steel. Two unknowns, but you have only one equation of equilibrium, sigma m is equal to 0. Second one is the curvature or the radius of curvature of two bent up beams is same. That is a compatibility condition. So, flitched beams ds is 1. Unknowns are 1, sigma m is equal to 0 we have, but two unknown, this I think you have already known, sigma m is equal to 0 is one equilibrium equation and unknowns are stress in wood, stress in steel. So, one condition, what is that condition you have taken flitched beams? Equilibrium equation is this one, moment of resistance is equal to moment of resistance of steel plus moment of resistance of wood. This is external equilibrium equation. Compatibility condition, what you have learned, radius of curvature of wooden beam is equal to radius of curvature in steel. So, solving 1 and 2, or this one you have already solved, why we should write. Okay. Next, in two examples are enough. In structural analysis, third point, two hinged arches you have taken. This comes under force method. Two hinged arches where ds is 1, we have told you. Then in this case, compatibility condition you have taken. What is that compatibility condition? You see, compatibility condition is given by Castigliano's theorem 2 because it is a linear elastic arch. From Castigliano's theorem 2, you have calculated relative displacement of AB is equal to dou u by dou horizontal thrust is equal to 0 you have taken. If it is 0, it becomes principle of minimum strain energy or principle of least work. If relative displacement of two arch supports is not 0, simply Castigliano's theorem 2. You cannot call it as principle of minimum strain energy is equal to 0. So, this is the compatibility condition you have taken. So, theorem 2 comes under force method of analysis. So, theorem 2 comes under force method of analysis. Accordingly, we can take it as another things are what? The Crotty-Engesar theorem. In this particular case is principle of minimum complementary energy. In this special case is Castigliano's theorem 2. It is applicable to linear, non-linear. If applied to linear, it becomes like this. If it is applied to linear elastic structure, minimum complementary energy becomes principle of minimum strain energy. Principle of minimum strain energy or principle of least work all come under force method of analysis. Why force method of analysis? Because dou u by dou x or dou u by dou h, because strain energy you are differentiating with respect to force, then what you get is the minimum strain energy. Dou u by dou h means Castigliano's theorem 2. So that means it is a force method of analysis because forces are unknowns in that method. A set of compatibility conditions we are getting. Okay. So this is about two hinged arches. Next, another method we have studied 1, 2, 3. Fourth one I am writing here because already it's full. This will leave it. Another force methods that we have studied is theorem of three moments. Third one, fourth one is theorem of three moments. Here also you will take compatibility condition developed by Clapeyron. Compatibility condition, what he has how he has developed is, in a continuous beam, he took the slopes theta BA is equal to theta BC at an intermediate support of a continuous beam. Slope at one side is equal to slope at the other side. Otherwise, it means that the beam is broken. So at one side, whatever slope is there, other side also same slope should be there. So otherwise, the beam is not continuous; it is broken. So using this condition, he has given theorem of three moments, Clapeyron. Since he took the help of compatibility conditions, so it is also come under force method of analysis. Okay. Then method of consistent deformation. Earlier sometimes we call it as method of consistent deformation. Nothing but compatibility conditions only. Consistent deformation means deformations are inconsistent with continuity of the structure. Here also consistent deformation or compatibility means AC member if it elongates by 10 mm, BC member must contract by 10 mm only. So that means deformations are inconsistent with the continuity of the continuity of the structure. That's why consistent deformation also we call it. Then flexibility method. Flexibility matrix method. Actually, this flexibility matrix method means Castigliano's theorem 2, you will get a set of compatibility conditions. Those compatibility conditions you write in a matrix form, then it becomes flexibility matrix method. But comes from theorem 2 only, Castigliano's theorem 2. In all these cases which we have studied in strength of materials or two hinged arches, or you are going to study in matrix methods, ds value must be less. Suppose ds is 1, then you require only one compatibility condition as in those problems. As ds increases, number of compatibility conditions also increase, our work also will increase. So force methods of analysis are useful if ds is less. Quickly we can get out of the problem. So suitability of these methods are when ds is less. Not. When ds is less, then these methods are suitable. Okay. So this is whatever you have studied in strength of materials and in structures, force methods is this case. Now let us see the displacement method or stiffness method of or equilibrium method. This part I remove. Okay. Now we'll see the characteristics of the displacement method. Its characteristics. In this case, we take displacements. General term it is. Displacements means slopes and deflections are taken as unknowns. And equations are expressed in terms of these unknown displacements. You can say that is slope deflection equations. Then this what in the slope deflection method we have done. Then additional equations, or we can say additional internal joint equilibrium equations are developed these internal joint equilibrium equations you will get from Castigliano's theorem 1, or by MBA plus MBC is equal to 0 also we can write it. That means energy theorems when you are taking theorem 1 is useful. Otherwise our ordinary manual calculations. Giant equilibrium equations are developed to find the unknown displacements. I write the next one here to find the unknown displacements. In this case, example. Now, examples when we see without using the energy theorems, this is what we have done. First thing you have learned was under the stiffness method, slope deflection method. The slope deflection method developed by Manny. Then whose iterative version moment distribution method came, because when calculators were, I mean, computers were not there, 1960s like that, slope deflection method, you get 10 simultaneous equations, say. Solving 10 simultaneous equations used to take a lot of time. So the Hardy-Cross came into picture and he has developed moment distribution method. Hardy-Cross. This is iterative, this is the successive approximation. It is called method of successive approximation of slope deflection equations. So from the slope deflection equations only, this moment distribution method came. Later on, one more person, Kani's method. Kani has given another version. It is the iterative version, which we have not discussed because unlikely to come in the exam. So iterative version of slope deflection equations. He has given that Kani's method. Iterative version of slope deflection method. Then you have stiffness matrix method. The stiffness method comes from Castigliano's theorem 1. Energy method, we can take it from the Castigliano's theorem 1, that means that is energy theorem. By differentiating the strain energy with respect to displacements, not forces, you will get the forces. Then accordingly, stiffness coefficients are developed and you write them in a matrix form. Okay, so stiffness matrix method, it is matrix version of slope deflection method. This way we can use it, or derived from Castigliano's theorem 1. Stiffness matrix method comes from Castigliano's theorem 1. Now, in all these methods, if at all dk, kinematic indeterminacy, a set of equilibrium equations you will write in the matrix method. If at all number of independent displacements are less, now the additional joint equilibrium equations also will be less. Means external equilibrium equations are same in both the methods. The additional internal joint equilibrium equations, which you get from Castigliano's theorem 1, those equations will be less if dk is less, kinematic indeterminacy is less. If that dk is 0, say, then the everywhere you will get a set of simultaneous equations with 0 displacement itself. So if dk is less, then these methods are useful. Then these methods are suitable. Okay, this is the thing. That means in the exam they will ask you whether dk is less or ds is less. First you have to calculate. Accordingly, select which method is suitable. Let us see how the numericals come. This is the overall entire history of what we have studied in strength of materials and in structural analysis. Energy methods I have given you completely, whatever we have studied. Some come under force method, some come under displacement method or stiffness method. There are Castigliano's theorem 1, theorem 2, that's it. In our BTech level, we have only the linear elastic structures. That's why the Castigliano's theorem 1 and 2 are enough. Crotty-Angasar theorem, we don't have to use. We never used it because we didn't deal with the material nonlinearity or geometric nonlinearity in BTech level. Now see, on this how the questions come is this way. The most suitable method to analyze the structure shown in figure. See here, there is one a plane frame subjected to is a truss structure actually because all of them are links. This point let us say A, B, C, D. Okay. First one is MDM. Second one, slope deflection method. Third one, strain energy method. None. So, which method is suitable depends on ds and dk. If at all ds is less, force methods you have to select. If dk is less, then stiffness method you have to select. So, ds and dk, you have to find this one. So, ds, in ds, first method, you can take ds is equal to r minus s, number of reactions minus number of equations of equilibrium. Our total static indeterminacy, if we wanted m plus r minus 2j. Number of members are 3, number of joints are 4. Unknown reactions are 6. Complete reactions, because 2 reactions we are counting HB, VB, HC, VC like that. So, members are 3, number of reactions are 6. 9 minus 2 into J is 4. So, 9 minus 8, 1 degree. So, ds is 1 degree. Suppose you don't want to use this formula, you want to take simply r minus s, number of unknowns minus equations of equilibrium. How many unknown member forces are there? If you take joint A, only 3 unknown member forces. If I know 3 member forces, HB, VB resultant, RB has no choice. It has to be in the line of the member only. Here, HCVC resultant has to be vertical only. HC must be 0. Then VD-HD resultant reaction must be FAD only. So, total number of unknowns are actually 3 only. If I take unknowns as 3, equations of equilibrium is joint equilibrium 2. You will get 1 degree. So, what are the unknown reactions 3? What are they? Force in the member AB, force in the member AC, force in the member AD. If I know these three member forces, I will find everything. Equations of equilibrium available are only two. What are they? At joint A, because only three members you are taking. At joint A, we have sigma x0, sigma y0. So, at joint A, three unknowns are there, two equations of equilibrium. So, one unknown extra. All other reactions you can find if you know the member forces. In the exam, whatever idea you get it, either this way or this way you can find. So, ds is 1. dk. What is dk? Number of independent displacements. What is dk here? Because since it is a truss axially loaded member, dk is 0. Rotations we should not count. Here also dk is 0. Here also dk is 0. But here dk is 2. What are they? Displacement of A in x direction, displacement of A in y direction. So, dk is 2. Delta Ax, delta Ay. Since ds is less, you should not select the stiffness method. MDM, stiffness method. So, we should not take it. SDM, slope deflection method, also stiffness method. So, we should not select. Then left out is strain energy method. Since ds is less, force method. In the strain energy method, you take the forces are unknowns, what we have told you earlier. Force method is suitable. Force method, that is strain energy method, is suitable. For statically indeterminate structures, ds is equal to 1. Indeterminate trusses, I didn't give you any numerical example because within the stipulated 2 minutes time we cannot solve, because this is what you have studied. In the mains, when you come back, I will again tell you all the cases. How to find the redundant force? This is the case. Redundant force is equal to FAC, let us say, X, that you call it as X, minus summation of PKL by AE by summation of K square L by AE. This is one formula we derive from the compatibility condition. Derived from compatibility conditions. So, it is a force method. Okay. This in the 20 marks, why we have not explained these forces is, within 2 minutes time, you cannot find member force. First you have to find force in the members, then you have to find K values, then you have to square them, then tabulate them, and then this division means it will take minimum 6 to 7 minutes time. So, such compatibility conditions for the statically indeterminate trusses we didn't give. Lack of fit, etc. What's the compatibility we have told you? That means one will bend at tension. If the lack of fit is there, say, in particular redundant member, then that will produce forces in the members. Those nature of forces, whether tension or compression, I have told you. How to calculate them, I have not given, because in the stipulated time we cannot solve them. Once we come back for mains, I will explain to you how this equation is derived. Okay, like this. Now, having understood the overall methods of analysis, etc., now we will deal with the stiffness matrix method and flexibility matrix method.